The first talk will be titled Counting the Number of Integer Points of Non-Parametric and Parametric Polytopes with the PolyhedralSets library in Maple. It will be given by Yuzhuo Lei, and his collaborators are Rui Zhuanjing. Yuzhuo Lei is from University of Western Ontario in Canada. His collaborators are Rui Zhuanjing from Jiangsu University in China, Christopher Maligak, and Mark Marina Mahsa, also of the University of Western Ontario, and Eric Postma from MapleSoft. Please go ahead.
Thank you, Austin.
And welcome.
Okay. Thank you, Austin. And good afternoon, everyone. My name is Yuzhuo Lei, and this afternoon, it's an honor to be discussing counting the number of integer points of non-parametric and parametric polytopes with PolyhedralSets library in Maple. So let's get started. And, okay, so here's the background. The PolyhedralSets library was integrated in Maple in 2015, which is regularly enhanced with new features. And this library is dedicated to the study of rational polyhedral set, which is the solution set of systems of multivariate linear inequalities. And in many applications like discrete optimization and the program analysis, one needs to deal with the integer point of polyhedral sets. To this end, the PolyhedralSets library can provide different tools which will be discussed in this talk, including the computation of integer whole, the solving for the integer points of polyhedron using lattices, and the counting the number of points of non-parametric and parametric polyhedral sets. So the first part is to compute the integer whole. So here's some definition. A convex polyhedral set is given by this relation, the AX less equal to B, where A is a matrix and B is a vector. The integer whole of P is the smallest convex polyhedral set that containing all the integer points of P. As you can see here, the red region is the integer whole of the blue polyhedral set in 2D. So how do we compute the integer whole? The first step is the normalization, where the idea is that we shift the area facet of the input polyhedral set towards the center of the polyhedral set, then until the hyperplane of the facet hits at least one integer point. Then of course, this action will not change the resultant integer whole. And after that, we are going to compute an approximation of the integer whole. As you can see here, that's the red region. And since this is an approximation, there are some gap spaces that's left to be analyzed, like the green, the purple, or the blue area. So for these spaces, we are going to use the brutal fourth way, that is the Fourier-Morsky elimination, to analyze all the missing points in those gap spaces. And finally, we are going to go apply the quick Hall algorithm to obtain the final integer whole. And sometimes the result can be quite complex. For example, here, if we are given this input, the pyramid in 3D, its integer whole contains 139 the vertices. And right now, I'm going to show a demo that shows how we compute the integer whole. As you can see here, if we are given the triangle in 2D, the purple region that's the integer whole that we compute using the command integer whole. And also in 3D, if we're given a tetrahedron, that is the pink tetrahedron, the blue region, it's integer whole. And moreover, in the 3D, if we are given an dodecahedron, as you can see here, the pink, that's the input, where the blue region is its integer whole. And of course, we can also do the higher dimension, but we cannot visualize them here. So next, I'll be discussing the Z polyhedral sets. So the Z polyhedral library was a new package that was introduced in Maple 2.3, which was used to describe the integer solutions to system of linear inequalities, as you can see in this picture. And how do we compute them? Well, the basic idea is to eliminate the variables one after another, which is equivalent to projections onto the lower dimension. And it will stop until we obtain a sort of the triangular shape. And for example, here, if we are given two inequalities, the system for P, the Fourier-Morsky elimination can compute the real projection or the real shadow that is given by this formula. And this is a irrational polyhedral. However, we have one more projection that can do better. That is the dark shadow computed by Delmar test. The dark shadow can ensure that each point in the projection is the image of at least one integer point in the original polyhedron. And as you can see here, comparing to the real shadow, the dark shadow was adding one extra term that was highlighted in the blue color. And as you can see here, if we are given the red polyhedral set, the whole area, that's the real shadow, where the blue region, that's the dark shadow. However, there are some missing spaces left. For those spaces, we call them the gray shadow. And for the gray shadow, we are going to use a combination of the exhaustive searches and recursive calls to analyze the missing point in the gray shadows. And let's go back to the Maple again. And I would like to show another demo that shows how to use the Z polyhedral library. As you can see here, we are given the pink triangle in 2D, and those points are the points that we can go apply the Z polyhedron to represent. And also in 3D, that is the same idea here, where you can see here, the blue points are coming from dark shadow, where the green points are coming from the gray shadow. So last but not least, if we want to compute the number of points of parametric polyhedral, one challenge is that not only the size, but the shape of the polyhedral set can vary. For example, if we are given this P, the parametric polyhedral set, with the variables I, J, and the parameters N, when N is 8, 10, or 12, the shape of the polyhedral set can vary. As you can see here, the third one, and the first one has a pointy top, where the second one has a more flat top. But fortunately, the Euler theory can tell us that these variations are periodic. Hence, we are going to apply a piecewise function to show the number of points. Okay, so here I'm only going to discuss the non-parametric case, but with parametric case, you can refer to our paper with Maple. So for non-parametric case, so every polyhedral set is associated with a Lorentz series in n variables, which we call the generic functions. And if P is a polytope, then we have the G equal to the number of points. And moreover, if P is an unimodular and the symmetrical cones, then computing the function can be easy. But otherwise, we need a few reducing steps to.
There is less than 1 minute left. So
okay. So yeah. So if I want to compute the general function, the Brown's formula can state that the sum of polyhedron is the sum of the corners, and we can decompose the cones into the symmetrical cones, and Bahrami algorithm can decompose any cones into unimodular cones. So finally, I have the one last example that shows how do we compute a number of points of parametric. The input is a parametric polyhedron with ij as variable, and the mn are parameters, and the results contain 4 cases, and if we plot them, the result. Yeah, thank you, and that concludes my talk. Thanks so much.
Thank you, Yuzhuo. Do we have time for one question?
I think we don't
okay.
for this talk. We move on to.
We're going to have to move on to the second talk then. Second talk will be by Dr. Hari Sitaula from Montana Tech University. Yeah, please go ahead and you can introduce the title of your talk.
All right, this is me, Hari Sitaula from the university, from the Montana Tech University. And I would like to welcome you all in this short talk where I am going to discuss on the algorithm to compute discrete residues of a rational function. This is a excuse me, collaborative work with Dr. Carlos Arache from the University of Texas at Dallas. And this presentation is based on the research published in IJEC 2024 and is partially supported by the NSF grant. So let's start with the motivation. To motivate this talk, I would like to introduce the notion of continuous residue of the rational function that has been in use since long for necessary and sufficient condition to test the rational integrability of a given rational function. For this, let me consider a rational function in a field with the characteristic 0, and let me write the rational function in the partial fraction decomposition form in this form, where this p of x is the polynomial, and of course this is the rational part of the rational function under consideration, and the c sub k of alpha are going to be 0 for almost all values of alpha and k, because we are summing over infinity, and we all know any rational function cannot have infinitely terms in it. Then, as I mentioned earlier, the continuous residue of the rational function can be used to see whether this rational function under consideration is rationally integrable or not. In fact, the rational function is rationally integrable if and only if the continuous, or let's say the classical residue of the rational function of order 1 for each value of alpha are 0. Otherwise, the rational function under consideration is not going to be rationally integrable. This is what we have been practicing since long. Now, back in 2012, Chen and Singer created the notion of the discrete residue of the rational function, which is analogous to the continuous or let's say classical residue of the rational function, but there are some differences. For example, integrability in the continuous case is replaced by the summability in the shift case, and the other traditional derivation operator has been replaced by Q dilation operator in Q discrete case. But because of time restriction, I will not be able to discuss about the Q dilation case and the Q discrete residue of the rational function. So I will be discussing about the algorithm to compute discrete residue of the rational function in shift case. So before jumping into the algorithm, I think we need to define what the discrete residue of the rational function precisely means. For this, let me consider the same rational function that we considered earlier, but let me rewrite the complete partial fraction decomposition of the rational function. Furthermore, decomposing the given rational function on the basis of orbit. That means I'm making the horizontal slices for the given rational function, where I mean the orbit, let's say the G orbit is nothing but this set. I mean, if we are computing the orbit of alpha, then this is alpha plus some integer, and I mean this n is some integer. Then the discrete residue of the rational function in the G orbit of omega is denoted and defined by this command. Okay, and then here is a proposition proposed by Chen and Singer back in 2012, which is very analogous to the necessary and sufficient condition to check the rational integrability of a rational function in the classical scenarios. But here, the rational integrability is replaced by rational summability. In fact, a rational function which is in this form is rationally summable if and only if the discrete residue of this rational function f in any orbit omega and any order k is 0. That means the discrete residue of this rational function in any orbit and any order equals to 0. This proposition is important in the sense that if we have to compute the certificate G, then oftentimes computing this certificate G is impossible, and the rest of the time computation of the certificate G is going to be expensive. So without computing the certificate G, we can determine whether the given rational function is rationally summable or not by using the sufficient and necessary condition proposed by Chen and Singer. Now, there is a challenge. The challenge is if we want to compute the discrete residue of the rational function from this definition, then one need to find the complete partial fraction decomposition of the rational function. And as we all know, finding the complete partial fraction decomposition of the rational function is computationally expensive. So what we did here is we try to compute the discrete residue of the rational function without finding the complete partial fraction decomposition of the rational function, but we just use some GCD computation and basic linear algebra. So in that sense, you can say the algorithm that we develop for the computation of the discrete residue of the rational function are efficient and practical to compute the discrete residue of the rational function. Okay, so before discussing about the computation of the discrete residue of the rational function, let me very briefly discuss how we compute the continuous residue of the rational function. For this, if a rational function f is given, then by using the Hermite reduction, we can reduce the given rational function in the proper form where the degree of the denominator is greater than the degree of the numerator, and denominator and numerator are co-prime to each other. Not only this, the numerator of the rational function under consideration is square free, meaning it has no repeated root in it. So to compute the continuous residue of the rational functions, we have been using the Rosten-Traeger resultant of these two polynomials. And if we evaluate this polynomial at the root of, let's say, pole of the given rational function, then these are going to be precisely the first order classical residue of the rational function. That means if we want to compute the classical residue of the rational function, then we can just compute this Rosten-Traeger resultant. And Rosten-Traeger resultant of two polynomial can be computed by computing the determinant of the Sylvester matrix. So computing this pair of the polynomial, I mean, this B of x is already given if the rational function is given, and computing this R of x is just as good as computing the complete first order residue of the rational function. I mean the continuous residue of the rational function. So we are trying to find B of x. Instead of B of x and R of x, we will find similar type of the polynomial having some properties. So, and on the basis of the polynomial that we evaluated by using the algorithm, we would be able to find the discrete residue of the rational function. This is this is our main goal. I mean, we would like to compute bk of x and dk of x, which is analogous to the computation of the continuous residue of the rational function, but bk of x and dk of x should satisfy some basic properties. For example, bk of x contains precisely one root on alpha from each orbit omega, and then the discrete residue of the rational function f on the same orbit of same order is not going to be 0. And if you evaluate the dk polynomial at the root of this bk polynomial that we evaluated by using the algorithm, then it should give us the precise discrete residue of the rational function on the same orbit of same order. So, I mean, there are sequence of algorithm, and because of time constraint, I will not be able to go over each and every algorithm, but here is the tentative overflow, workflow of the algorithm. The input is the proper rational function, and output, the expected output is these order pairs, let's say order pairs of bk and dk, where the bk and dk satisfy the property that I discussed in previous slides. So here are the sequence of implementation. First, we apply the Hermite list algorithm to get this output, FIs, where this M is the highest order pole of the given rational function. So the Hermite list algorithm is going to terminate after m many iteration. And to apply this Hermite list algorithm, we can use hyper-exponential function in Maple. And then once we got this list, I mean, this is the list where the denominator of each of the rational functions f1 up to fm will be square free. That means it will have just non-repeated roots. And then after that, there is another algorithm, which is simple reduction algorithm. We apply simple reduction algorithm to each of fk that we obtain by applying the Hermite list algorithm to the given original rational function, and we will get f bar of k. F bar of k will have some further properties, like it will have square free and shift free denominator. And then we'll apply this fk, I mean f bar of k, I mean this first residues algorithm to each of f bar of k to get bk and dk that has the properties mentioned earlier. And I'm sorry, I'm not able to go over each and every steps in this algorithm because of the time constraint, but yeah, this should be available. This is available in archive, so if you want, you can read about the this sub algorithms, I mean the algorithm of algorithm there. Okay, and then here is a numerical example. This numerical example has been adopted from the paper by Malam and Subramaniam and Pirastru, because it will cover different scenarios. For example, in this small example, there are two orbits, and the order of the largest order of the pole is 3. So if you apply the Hermite list algorithm, it will produce 3 rational functions, f1, f2, and f3. For example, you will get f1 to be this one, f2, and then f3. So the rest of the algorithm, I will just apply to f1, because the rest process is going to be similar. So if we apply, let's say, rest of the algorithm to this f1, then it will produce b1 d1 to be b1 to be this polynomial, and d1 is going to be this polynomial. So this is a trivial example. So you can find the complete partial fraction decomposition of the rational function to check what are the discrete residues at each pole. For example, if you compute the discrete residue at the pole, let's say alpha equals to 0 of order 1, this is going to be this one, and then at same orbit but different pole, the discrete residue is going to be, pole is negative of 2, it is going to be 1 over 250, something like that, and first order but the different pole, this is going to be discrete residue. And then if you sum this all, it will give you the discrete residue in
a minute left.
Yep, sorry. Yeah, I am almost finishing. If you sum all this, then it will give you the discrete residue of the rational function of order 1 in the orbit of this orbit. So, and this is directly given by computing the polynomial d1, which is here at the orbit of alpha equals to negative of 3. Instead of computing this all, you just can compute d1 of negative of 3 to get the discrete residue of the rational function. Thank you.
Well, thank you, Dr. Sitaula, for that very interesting talk. Do we have time for one question?
I think we have to skip.
Okay.
Again.
Okay, sorry. We'll continue to the next talk then. The next talk is going to be given by Juan-Pablo Gonzalez Trochez from University of Western Ontario with collaborators Manuel Romero, also of UWO, Matt Calder and Eric Postma at MapleSoft, and Mark Moreno Mahsa, also at the University of Western Ontario. The title is Power Series Solutions of Algebraic and Ordinary Differential Equations with a Multivariate Power Series in Maple. Please go ahead and welcome.
Thank you, Austin. I will share my screen now. Can you see my screen?
Yes.
Okay, perfect. So today I will be giving this talk, as Austin already presented the title and my collaborators. I will skip this part. So this is the agenda for today. First, I will do a short introduction. Then I will talk about power series, then power series solutions of ODEs, and later on power series solutions of algebraic equations. So the following people have contributed in an indirect or direct way to the MultivariatePowerSeries package in Maple. So I think it's important to mention them, as you can see them here. The introduction. So power series are very important structures in mathematics, but they are potentially infinite structures, and this represents a challenge computationally speaking. Conventional encoding of power series is performed by providing a truncation degree before the computations are done. So in case we want to increase this truncation degree, we need to redo all the computations. The multivariate power series package in Maple overcomes this limitation by using the lazy evaluation scheme, which only computes things when needed and just once. Power series can be used to compute approximations of ODEs and algebraic equations, and that will be the main topic of today's talk. So power series. let's denote A as the ring of multivariate power series in the variables x1 through xn over an algebraically closed field A. A formal power series of this ring is just a formal sum over all the possible multi-index E of a constant A sub E times x to the E, where x to the E is just the product of xi to the EI for I from 1 to n. The homogeneous part of degree k of a formal power series F is just the sum of all the terms in the power series such that their degree is equal to k. We are able to define polynomials with coefficients as power series. For short, we will call them UPOPs. And the form that they have is like this. We have a polynomial in the variable y, and the coefficients will be a multivariate power series. So our lazy evaluation scheme allows the users to compute terms on demand, increasing the precision as needed. To implement this scheme, we require the following. First, an update function, which is in charge of computing the homogeneous part of a given degree. Second, we ask that we're able to store the required information for the update function to work. In this case, we call these ancestors. And finally, we store every homogeneous component that we compute. As an example, if we want to add two power series G and H, the ancestors of the power series F will be G and H, and the update function is just a function that is in charge of computing the homogeneous part of G of degree K, and the homogeneous part of degree K of K is add this and store it. As a first remark, it's important, I would like to mention that addition, multiplication, power series inversion, between others, are continuous functions in the crude topology. And this is just a mathematical justification of why lazy evaluation works in this for the multivariate power series package. As a second remark, if we're in the univariate case, Lagrange series are the fraction field of the ring of formal power series. And furthermore, if the base field is C, then the Puiseux series are the algebraic closure of the field of Lagrange series. We mentioned this here because the Puiseux series can be seen as a generalization of the power series. Furthermore, when we have a UPOP, we know that we can completely factorize this into linear factors over the field of Puiseux series. Now, power series solutions of ODEs. The main goal of this part of our work was to, given a linear ODE with univariate polynomial coefficients and some initial conditions, we want to compute the power series solutions of this ODE around the origin. As it's important to mention also that we want to expand this to work with linear ODEs with univariate function coefficients. In particular, we wish to be able to handle linear ODEs with power series coefficients of our package around a point different at the origin. Now, if I go now to my worksheet, as a first example, we can consider this linear ODE of degree 2, where we have all the necessary initial conditions. We can call the multivariate power series package the command power series with this information together with the independent and dependent variables, and we get a power series object back. We're able to compute the terms of this power series object up to a given degree using the truncate command, as we can see here. As a second example, in this, consider this ODE where we only have some initial conditions. The power series command will be able to accept this information and compute the power series solutions, but note that the missing initial conditions are considered as a constants here. Now, if I go back to my slides, we have now power series solutions of algebraic equations. As an introductory example, consider the polynomial f that we can see up here. the regular chains package of Maple is able to currently compute approximations of the solutions of F around the origin with the branches command. If we send this polynomial to the branches command, we will get this here back. And as we can see in this plot here, the polynomial F in blue will be properly approximated around the origin by the curve in green here. I would like to do a small remark here. This is a polynomial of degree 2. So we expect to get 2 branches, but the regular chains package currently only returns 1 branch. And this is because the second branch is a branch that will go to infinitive when we go near the origin. And for that reason, the package is not returning this other branch. Now, the aim of this part of our work was to enhance 2 commands of the regular chains package, the regular chains branches command and the limit points command using the MultivariatePowerSeries package. So for that, we added options to the 2 commands. For the regular chains branches command, we added the option to choose between different factorizations algorithms from the MultivariatePowerSeries package. That is Novak formulation of the Newton-Poisson theorem and the extended Hensel construction, and the original algorithm that is inside of the regular chains package, which is the same extended Hensel construction that we have here. The difference between these two is that this, the extended Hensel construction of the multivariate series power package works in a lazy evaluation. That means that we will get power series object backs, and we can increase the precision of this object as much as we would like, without redoing all the computations. Now, the second thing that is important to mention here is that now we will be able to compute all the branches, even the branches that go to infinitive, when we call Novak's formulation of the Newton-Poisson theorem. It's a constructive proof, this algorithm. That's also key for our package. And finally, all the commands, we call the regular chain branches command with one of the factorizations algorithm from the MultivariatePowerSeries package. Then we return power series object or Poisson series object. As I mentioned before, we are able to improve the approximation as much as we would like with these objects. Now, the Newton-Poisson theorem says that if the field of formal Poisson series over C is the algebraic closure of the field of Lorentz series over C. We have 2 different flavors of this theorem inside of the MultivariatePowerSeries package for the computations of UPOPs. The first one is Novak constructive proof of the Newton-Poisson theorem, which relies only in a transformation and basic arithmetic operations in the field of Poisson series. And the second one is the extended Hensel construction, in which Poisson series are implicitly manipulated as power series and a change of variable. Now, finally, the second goal of this part of our work was to compute limit points of a space curve. To be precise, we wanted to compute the limit points of a 1-dimensional regular change, which is just a special set of polynomials under the Zariski topology. That is, we want to compute the limit points of the quasi-component of a regular change R. I will go into more details of this in my worksheet. So, as I mentioned before, we have different flavors of factorization of UPOPs. So if we construct a UPOP P like we have here, we can call, let's say, Hensel factorize. This is just a normal Hensel lifting algorithm. As we can see here, for this particular example, we get the same polynomial back that we are not able to factorize in this case. Now we can call, in this second example here, with the same polynomial, we can call Novak's version of the Newton-Poisson theorem. And as we can see here, we get linear factors back. finally, we can call extended Hessel construction of this polynomial, and we see that in this case we also get linear factors back. But notice that this will not always be the case, as we will see, as we saw with the this is the case also. This is always the case here. Sorry. Now, about computing branches, as we can see here, we have a polynomial f, the same polynomial that we have in the slice. And we can call the branches command with this polynomial. This is the classic algorithm. We say that we get just one branch back here. This is just a normal polynomial. We can run the same command, but now adding the option factorization equal EHC. And we see here that even though we get the same polynomial, what we are really getting here is just a power series object. And we can do the same now, but with the option Novak, and we see that we get two branches in this case. It's important to mention that in these two cases, we are returning power series and Puiseux series objects. And we will be able to increase the precision of this approximation as much as we would like to, as we see in these two lines in here. Now, finally, about the limit points part.
I'll interrupt to say there's 1 minute left.
Okay. As we can see here in this example, we want to compute the limit points of this set of polynomials. And when we call the limit point commands, we are able now to do it using the MultivariatePowerSeries package, or without it, we get the same result. The only difference is that this is going to be slightly faster. What we want to see here is, as you can see, this polynomial here is when we approach 0, the initial of this polynomial, the leading coefficient, is going to explode because it's set. So we want to be able to study these problems around the origin, and for that is that we have these limit point commands. As you can see here in this plot, we have the point here, the limit point that we find. And here I have just a second example that is just slightly harder, where we get 4 limit points. That will be all on my side. Thank you.
Thank you, Juan. That was a great talk. Unfortunately, once again, we do not have time for questions. So we continue with Mahsa Ansari from Simon Fraser University, presenting computing the resultant and GCDs of multivariate polynomials over algebraic number fields presented with multiple extensions.
Hi, everyone. Can you hear me?
Yes, we can.
Yes, great. So I'm so excited to share my research with you, which is about computing the resultant of monic GCD and resultant of multivariate polynomials over algebraic number fields. Let me see. Okay, before exploring the algorithms, I would like to give you a brief overview of algebraic number fields and some essential background information. Let alpha 1 to alpha n be algebraic numbers. Then the algebraic number field Q adjoint alpha 1 to alpha n is the smallest field containing Q and alpha 1 to alpha n. Here we have a very important theorem which indicates that if alpha 1 to alpha n are algebraic numbers, then there exists another algebraic number such that Q adjoint alpha 1 to alpha n is isomorphic to Q adjoint gamma. We call gamma a primitive element. For instance, here in this example, a square root of 2 plus a square root of 3 is a primitive element for this field, Q adjoint a square root of 2 and a square root of 3. Maybe you ask yourself why it's important to compute resultants and GCDs. Okay, resultant and GCDs appear as subproblems of computing, of factorizing actually, factorizing polynomials over algebraic number fields, particularly if we want to use Traeger's algorithm. Moreover, we can use resultants to solve systems of multivariate polynomials and to use the elimination theory. Here is the list of our Let f1 and f2 be two polynomials over Q, two multivariate polynomials over Q adjoint alpha 1 to alpha n. We designed two modular algorithms. The first one is MRES, which computes the resultant of f1 and f2 with respect to a variable, let's say y. And the second one is MGCD, which computes the monic GCD of two polynomials, f1 and f2. Also, we could present a new formula for computing the resultant of two univariate polynomials using the monic Euclidean algorithm. We implemented our algorithms using Maple, particularly by using Recten, which is a Maple library for recursive dense representation for polynomials. We also computed the expected time complexity analysis for both of our algorithms and a partial failure probability analysis for both of them. But before diving into the algorithms, we need to know how to compute our Q adjoint alpha 1 to alpha n. Let L0 be Q, Li be Li minus 1 mod the ideal generated by Mizi, where Mizi is the minimal polynomial of alpha I over Li minus 1. And let us denote Ln by L. Then we have Q adjoint alpha 1 to alpha n is isomorphic to L. So in order to do the computation over this field, we only need to map operands into L and do the operation over L. Both of our algorithms, MGCD and MRES, assume that we are given the minimal polynomial, so we can construct L here. Here is the monic Euclidean algorithm, which returns either the monic GCD of f1 and f2 or fail. This monic Euclidean algorithm is run over a commutative ring. And as you can see, in the fourth step, we make the remainders monic. So if the leading coefficient of one of the remainders is not invertible over R, then this algorithm will fail. However, let's say the monic Euclidean algorithm does not fail and it iterates after L iterations. In that case, we can put R1, R2, which is F1 and F2, and all the remainders computed at step 6 in a sequence. In that case, we will have a polynomial remainder sequence, which we call it MPRS. Using MPRS, we could present a new formula for the resultant of two polynomials, F1 and F2, which are univariate polynomials over R. R is a commutative ring. We could prove this theorem, and also we designed an algorithm to compute resultants using this formula. Here is our MRES algorithm. Let F1 and F2 be two polynomials over L, which L is this field. And F1 and F2 are multivariate polynomials. Our MRES, as I said, computes the resultant of F1 and F2 with respect to the variable y. In a pre-processing step, our MRES algorithm eliminates fractions from the input polynomials. So F1 check and F2 check are two polynomials over LZ, which LZ is this ring here. After that, we reduce the coefficients of our input polynomials mod a prime p, which p doesn't divide the product of leading coefficient of minimal polynomials times the leading coefficient of F1 check. And now this is the key, this is the most significant part of the algorithm. And we call phi gamma. Phi gamma maps polynomials over LP, which is this quotient ring with multiple extensions, into their corresponding polynomials over LP bar, which is this quotient ring with single extension. Now, as we simplify the domain, it's time to compute the resultant. We use our PRES algorithm to compute the resultant. PRES is a recursive algorithm using evaluation and dense interpolation to compute the resultant. After computing the resultant, it's time to undo what we have done so far. So we call phi gamma inverse to map the resultant over LP bar, which is this single extension quotient ring, into its corresponding polynomial over LP. And then we need to reconstruct the rational coefficients of the resultant. So we call Chinese remainder theorem and rational number reconstruction to get the resultant. There is a very important question. Can we use any prime here for our phi p, or can we use any evaluation in our PRES algorithm? The answer is a very big no. But do I have time to elaborate on that? The answer again is a very big no. So I encourage you to use this QR code to take a look at our latest paper, which was published in CAST 2024, to get more information about how MRES works. Here is the first benchmark. Let L be this algebraic number field, and let F1 and F2 be two polynomials over L with degree M. M denotes the degree of F and F1 and F2 in X and Y. And let MRES1 be this call be the timing for our MRES algorithm, at which we use phi gamma. And let MRES be our MRES without using phi gamma. As you can see, when the degree of the polynomials is getting bigger and bigger, if we use phi gamma in MRES, the time is by far faster than when we don't use it. In this benchmark, we changed the degree of polynomials, but here we have another benchmark which we changed the degree of the algebraic number field. And again, as you can see, when we use phi gamma, the timing is by far faster when we don't use phi gamma. Here is our MGCD algorithm. Again, we use the same procedure as our MRES algorithm. However, here PGCD computes the monic GCD of F1 and F2. And again, PGCD uses evaluation and dense interpolation to do that. The question is, can we use any prime for phi p? No. Can we use any evaluation point for PGCD? Unfortunately, no. And I am not going to talk about them because of the time limit. But if you want to get more information about how our MGCD works, please use this QR code to take a look at our previous paper, which was about computing monic GCD of multivariate polynomials over algebraic number fields. Here is the benchmark for our MGCD. Let F1 and F2 be two polynomials over L, which L is this algebraic number field with degree 32. Here again, MGCD1 uses phi gamma to map polynomials over multiple extension quotient rings into their corresponding polynomials over a single extension quotient ring. And here is the MGCD2, which doesn't use phi gamma. As you can see, when we use phi gamma, the time that we need to put for PGCD is by far less than when we don't call phi gamma. Here is a demo of our MRES algorithm. We, as I said, we used a Rekden library to present polynomials. It's a recursive dense representation for polynomials. Primitive this file, primitive, reads our phi gamma, and MRES here reads the code for MRES and PRES. Let M1 and M2 be the minimal polynomials of our algebraic number fields, and F1 and F2 be those two polynomials that we want to find their resultant with respect to x. As you can see, F1 and F2 are two polynomials over Q adjoint a square root of 3 and a square root of 2. When we call MRES, our code give us actually prints the problematic primes as well. I didn't talk about them, but I encourage you to take a look at our papers. That's my talk. Thank you so much for your attention.
Thank you, Mahsa. That was a very interesting talk. Does anyone have any questions?
I see a question in the comments.
Yes.
I'll read it out. Not to ask about the detail of which primes are allowed, I note that the CRT is in use, the Chinese remainder theorem, so multiple primes. Alan suggests that p-adic constructions might work better, especially if an allowed prime would allow p squared or p cubes to also be used. Is there a reason to use Chinese remainder theorem rather than p-adic?
We haven't tried the p-adic yet, but it's a good idea. Thank you so much for suggesting that.
All right, thank you. I didn't know whether or not there was a reason to avoid it because of the reconstruction in which primes are bad.
Okay, I can do I have time? How much do I
have? We have about a minute and a half left. So
okay, great. So some primes will okay, let me go back here and show you, for instance, here. P is when we use 11, then in our monic Euclidean algorithm we will face a zero divisor prime. So in our monic Euclidean algorithm, let me go back here. At this step we cannot make the remainder monic if we use p is equal to 11. So we don't use that prime. Also here I included an LC-bad prime. If we use p to be 23, then we will lose the leading coefficient of f1, and we don't want to do that because in that case we cannot reconstruct the resultant. So we don't use LC-bad primes as well. There is some other primes that I didn't
related to the extension, right?
cover. Yes, well done.
Okay.
Yeah, that's about the extension. We
Okay.
call them dead bad primes.
Right.
Yep.
Okay, thank you.
Thank you so much for your question.
Thank you. I think we better go on to the next talk now, which will be I think Sepideh Bahrami will be talking about computing osculating curves of power series in Maple with on behalf of collaborators as well, Taylor Brisiewicz, David Jeffrey, and Mark Moreno Mahsa, all of whom are at University of Western Ontario in Canada. Please go ahead, Sepideh Bahrami. And welcome to the conference. Yes, we can see and hear you.
Okay, thank you.
And your slides.
Thank you. Hello, everyone, and thank you for attending this talk. My name is Sepideh Bahrami. I'm a PhD student in computer science at Western University under supervision of Professor Mark Moreno Mahsa. And today I will explain about osculating curves and the way that we can compute them by using Maple. So, excuse me. Okay. So to begin, let's look at the problem we are addressing. The input is a plane analytic curve, which is locally represented near the origin by a power series, and it's specifically takes the form of f, which is the summation of ci multiply x to power I, and additionally we are given a positive integer d, which represents the degree of the polynomial we aim to compute, and the output is a polynomial fxy of degree d, and this polynomial is expressed as the summation of aij x to the power I, y to the power j, where aij's are unknown coefficients that we need to determine. And the key condition we want this polynomial to satisfy is that the f of x fx in mod xj, where j can be from 1 to nd, becomes 0. And nd, which is d plus choose 2 minus 1, is actually the number of unknown coefficients of the polynomial fxy. Just to recap, so our input is the power series fx and the positive integer d, and the output is a polynomial fxy that the polynomial satisfies the condition that we saw. So this means that we want to construct a polynomial that closely approximates the original curve fx, maintaining the correct behavior up to a specific order. But now let's see the intuition behind this process. VF denotes the zero set of f. So then VF is an algebraic curve, and it's the best possible local approximation to the input analytic curve at the specific point, in this case the origin, and in particular VF matches the curvature of the original curve y equal to fx at the origin. So what we're really doing here is finding a polynomial that hugs the curve as tightly as possible around the origin and capturing the curvature's behavior up to a specified degree. And as you see in the graph, osculating circles is one of the good examples of osculating curves with degree 2. And yeah. To understand how well our polynomial fxy fits the curve, we use the concept of contact order. So we say that the polynomial fxy has contact order k with the curve fx at the origin if f of x and fx, again mod xj, j from 1 to k becomes 0, but in mod x to the power k plus 1, it doesn't become 0 anymore. So essentially, the contact order tells us that how many derivatives of the polynomial and the original curve match at the origin. And as you see in these visualizations, show how the show osculating curves from degree 1 to 5 for the function fx. This is degree 1. This is osculating curve with contact order 1, contact order 2, this is 3, 4, and now let's talk about osculating spaces. So the osculating space of an analytic curve is the vector space of polynomials that have a specific degree and contact order with the curve at the origin. So formally, we define the osculating space VDK as the space of the polynomial fxy of degree d that have contact order at least k with the curve. And an important property of osculating spaces is that they are nested. As you see here, VDK plus 1 is the subset of VDK. So this means that as the contact order increases, the osculating space becomes smaller. Next, let's define what we mean by osculating curves. So again, let X be an analytic curve passing through the origin, and if f of xy is an irreducible polynomial without a constant term and the osculating space VDM equals the span of f of x y for some integer m, we call fxy the degree de-osculating curve of x at the origin. So in simpler terms, the osculating curve is the best polynomial approximation of the analytic curve at the origin and capturing its behavior up to a specific degree. And importantly, for generic functions fx, osculating curves exist for any degree d. This is guaranteed by the fact that the dimension of the osculating space is non-trivial for appropriate values of k, as shown by this theorem, and we have proved this theorem in our paper, which was presented in CASC 2024. And let's now discuss the first algorithm, which computes the osculating spaces. So the input to this algorithm includes positive integer d and k, and the polynomial part of the power series fx. The output is representation of the osculating space vdk of fx. Here is how the algorithm works. We define a general polynomial f dx y with undetermined coefficients. Then we compute the first k coefficients of the expansion of f dx fk minus 1x. And we set up a system of equations based on the condition that these coefficients must vanish up to order k. And then we solve this system by computing the null space of the resulting matrix, which gives us the osculating space. And the second algorithm computes the osculating curve itself. The input is the positive integer d and the power series fx. And the output is the osculating curve of degree d if it exists. So the algorithm works as follows. We set the initial value of k to nd and compute the osculating space v equal to vdk. And then while the dimension of v is greater than 1, we increase k and compute a new osculating space. So when the dimension reduces to 1, it returns the basis of v, which is the osculating curve. Now let me show you some examples of the algorithms that we have written in Maple. So here we want to find the osculating yes, here we want to find the osculating curve with degree 3 for the function cosine x minus 1. So as I run the code, we would get the polynomial f with degree 3 and contact order 9. And if we plot it, we would see that it's a good approximation with degree 3 for the function cosine x minus 1. And also for exponential minus 1, we run the code and we want to find the osculating conic for it. So we put d equals to 2, and then we get the polynomial f, which has degree 2, and if we plot it, we would see that it's a good approximation at the origin with contact order 5 as we expected for the exponential minus 1 function. And excuse me. And thank you for your attention. That was my talk.
Thank you, Sepideh Bahrami, for that very interesting talk. Do you any time for any questions? I think we do.
We have 3.5 minutes.
Okay. Are there any questions in the chat? No.
I had a question, if I may.
Okay, go ahead.
I was wondering, is this a process that is continuous in the Kroll topology? Let me rephrase that. If we take more terms of the of f, so if we increase the number of terms of f that we take, do the initial terms of the solution stay the same? Do we just get more terms at the end that are different, or do the lower order terms potentially also change?
No, actually, in our algorithm, we choose a truncation point for our Taylor expansion of power series F. So we get the same thing.
Right.
We have a specific truncation point.
Right. Yeah, I guess what I was wondering is, if you were to run your algorithm twice, once with a given truncation order and once with a higher truncation order, would the initial segments of the results agree, or would they be different?
That's a good question, actually. For actually that we need a fixed size for our polynomial system, which we find the osculating curve for it, and no matter if we change the truncation point, at the end we would get the same answer.
I see. Okay. All right. Thank you.
Okay.
I think maybe we should go on to the next talk.
Agreed.
And the next talk is given by Rafal Ablamowicz and Jane Liu, both Rafal formerly of the Tennessee Technological University, Jane Liu still currently at that same university. And it's called the MaterialConstants package version 034 Maple. And welcome to the conference, and please go ahead.
Okay, just a second. Okay, I'm in structural mechanics in the civil engineering. So today I'm going to present part one of our joint presentation with Dr. Ablamowicz on material constant package. So the part one will focus on the basic theoretical background. So the mechanics background for this package is in mechanics, the material constant matrix is often called C matrix or stiffness matrix in engineering. So the C matrix represents the elastic properties of the material in relation to the deformation under applied stress, commonly described through the stress-strain relationship or Hooke's law. So the mathematical representation, there is a two ways. The one is a tensor notation, another one is a matrix notation. So the matrix notation is commonly used in practice, in engineering practice. So we have to transfer the tensor notation stress second order tensor and epsilon, the strain second order tensor into a vector. So then we can determine the C is a 6x6 stiffness matrix. So why are the material constant important? Because through them, so we can predict the material's mechanical statics or dynamics responses. The number of a constant determines how the material reacts to the applied force or the deformations. So you can see this one. Let's say in general, the most general case, this is a full matrix. We have a 21 because the symmetric, so you will have 21 independent material constants. So that tells you if you apply the force in X direction, then if you have a full matrix, all the constant there, so you will generate 6 deformations. So they're all coupled. So it's hard to predict. So how is the number of a material constant in the C determined? Because not all the material has 21 material constants. For example, in here, so we use a monoclinic material. So this material, like ice, so is a type of monoclinic material. They have a one-plane symmetry. So that means if you have a material relative to X, Y, Z coordinates, then you have a relationship, let's say C matrix. Then relative to X prime, Y prime, and Z prime, then you have a C prime because the plane of symmetry. So therefore, those C's should be the same. So the C and C prime should be the same. So this TZ is a transformation matrix for this type of, if you have a X, Y plane is a plane of a symmetry. So let's say we have a tensor notation to use that transformation matrix, transform to the sigma prime coordinate system, then we put into array, into a vector. So then we generate this transformation matrix. So that is transfer the old stress in array to the new coordinates in array, the same as for the strain. So for this case, so we can see we use a C. This is the original C in X, Y, Z coordinates. So use this transformation matrix, we transfer to another coordinates because the plane of a symmetry, so therefore the C prime and the C are the same. So this is the original C, this is the C prime. So because they are the same, so then we can reduce the material constants. So we reduce from 21 to 13 for this material. So that tells us, you can see, for example, this is the stress, only the coupled with these two deformation. Otherwise, you have a 6, the difference. One stress will cause 6, the deformation. So that is why this zeros is very important. So 0 tells you reduce and decouple the certain type of relationship. Okay, so the part 2, Dr. Ablamowicz will provide a brief discussion on the algorithm for this package, how they programmed in Maple. Thank you. Okay, Rafal, you want to start?
I was interested in finding mathematics behind all of what Jane has just described to us. She's teaching a course in statics and dynamics, and from my point of view, mathematical point of view, we are talking about so-called standard materials, which are monoclinic, that have a single plane of symmetry, orthotropic, and transversely isotropic, which I'm going to define momentarily. And also there are certain non-standard materials. The farther you go down the list, the more symmetry the material has. The final trigonal, hexagonal, or trigonal, they have 3 planes of symmetry, and they are not necessarily orthogonal to each other. And also, all the transformations that we are dealing here with are given by orthogonal 3x3 matrices, which are either reflections in planes or there are rotations. So I wrote a simple package for Jane for the purposes so that she could teach the class and create examples for students and illustrate certain features of all of this entire theory. So the material constants package has certain known types, which I have defined, certain aliases, certain unknown protected names for certain reasons. The most important procedure is this particular procedure. These are called transformed material constants. And this is the procedure which essentially is intended to solve the equation that the transformed material constants matrix is equal to the untransformed, from which we get essentially a system of polynomial equations, which could be like 66 polynomial equations or more that we have to solve. So my goal for this presentation, I know I have maybe 4 minutes, is I'm going to go directly to the main procedure and show how exactly that equality equation between the transformed material constants matrix C prime equals to C is solved for the parameters. So I'm going to go to my second part where I want to illustrate the code. The procedure TMC, just a moment. So this is a step-by-step procedure to transform material constants. And in this example 4, I'm going to use so-called transversely isotropic material to illustrate in certain steps how the procedure works. The procedure essentially is an efficient way of solving a system of polynomial equations in a nutshell, for which I'm using Grobner basis twice. But I need to pick a certain order because certain indeterminates are going to need to be eliminated. And I need to, for the second computation, I need to pick a certain order, which is a convenience of the user that certain variables in the must be eliminated versus the others are kept. So, for example, let's consider, therefore, the first step. I'm going to consider just one single symmetry. This is the rotational symmetry matrix in the XY plane. And the sigma matrix is shown this way. The procedure TMC is a recursive procedure, which takes as an input to start with and the generic material constants matrix, which is C as a parameter. It is also using it for convenience as a first argument, whereas T1 through Tk are responsible for those are orthogonal matrices which describe the symmetry of the material. So you could, and then one symmetry matrix is applied at a time in a recursive step, so that the number of undetermined or general parameters in the C matrix is reduced. So in each step, the matrix C is reduced until, and then there's a k number of steps in this recursive procedure. So let's go over the steps implemented in the procedure. Step number 1, similarity transformation is applied to the stress tensor sigma with the rotational symmetry given by TT matrix shown above. I'm using only one symmetry, rotational symmetry in the XY plane, which is given by the TT matrix. And then you see the output. The sigma prime is the image, isomorphic image of that 3x3 matrix into a space R, vector space R6 that is used by engineers. Those are column vectors 6x1, which Jane described earlier.
There is 1 minute left in the presentation.
I have 12:50 according to my stopwatch. The T sigma matrix is essentially now applied to this particular, is using the transformation matrix TT and is creating matrix T sigma. And that transformation matrix is a composition of linear transformations. The transform material constant matrix is computed, C prime, as a 6x6 matrix. And here we are getting to the point where we have to solve this particular system of 66 polynomial equations where we have added certain additional indeterminates because we have certain indeterminates which are related by the Pythagorean law. So this system essentially of equations has to be solved for Cij. All right, now here we are adding the extra conditions. Those are the Pythagorean conditions. Now we are getting ready to apply Grobner-Basis method. So we are defining indeterminates in C, those are the ones. Then we are defining the reverse indeterminates, and the reason for that is that we want to essentially express coefficients with higher indices with those in terms of lower indices. We calculate the Grobner basis here's the Grobner basis calculation. I have 55 polynomials, and then I have to reduce this by eliminating polynomials which do not containCijk. I have then to then I have to compare because these polynomials are set up to 0. So for arbitrary angles, I have another system of 66 polynomial equations I have to solve. Well, I know that my time is now out. I'm done. So eventually we obtain, by solving the second time the system, we can substitute this into the original generic matrix C using the theory described by Jane, and we obtain the coefficient matrix, the constants matrix that looks like that. Anyone who is interested in having the worksheet, I will be happy to share it, either as a PDF file or as a worksheet, because at the bottom I have examples. I have altogether 14 examples where more complicated symmetries are used. Thank you.
Thank you very much, Jane and Rafal. I believe we don't have time for any questions on this talk. But thank you to all the speakers in this session. And I would suggest we're going to have a 15-minute break, and then there will be another invited talk that's called Series and Limit Computations in Maple. And that will be, I think, presented by Alan Witkoff on behalf of Jürgen Gerhard. So please join us for that at 3 o'clock. Thank you very much.